No, the other one.
Both of them.
Yeah,
I
the one that I
fell asleep a lot
chose.
this week.
Yeah, the one that I chose is.
Either of the perovskites.
All right.
Yeah.
So I'm just gonna. Yeah, I think it was great actually. So this paper is entropy-driven stabilization of multi-element halide double perovskite alloys. And there's a lot of thermal background basically. So like I would break it down a bit. So perovskite materials we know from crystals, they have the structure of ABX3, and I'll come to that. But basically the idea is like most of these materials have been used for solar cells because of their high.
Your laptop's
My
not
laptop?
blocking you.
Oh, okay. Okay. No worries.
Wait, maybe
Okay, I can just put it this way, right?
Yeah.
Yeah. Yeah, just put this guy here. Yep. Right. So most of these materials are used for solar cells. They have very good charge, fast charge carriers and all of those things. However, their major drawbacks are that most perovskites or most of the high efficiency perovskites use lead, which is toxic, as their B site, and most of them are also unstable. They are unstable in moisture and temperature. So Thomas and I were in a class last semester at Juan Pablo, and we're trying to actually just study perovskites for solar applications. Did I say solar space applications? Because
Space.
like in space you don't really have these moisture effects and stuff like that. That's currently
You got temperature though.
yeah, you have temperature, so we're studying like the effect, like the phase transformations that occur at different temperature zones and all of that. So you think about all these things. Now, this is the typical perovskite system. And so we have the halide perovskites, basically the X compound is made of the halide. So if I could do this, show the pointer, so then I can, yes, so it's ABX, so you have like the organic cation here in your octahedral site, and you have your halide, and then the halide is your X, and then the B, so this ABX. So halide perovskites have like halide as their X, right? And so they either have iodine, bromine, or chlorine. Now, because of the lead factor, most of these perovskites are trying to be made without lead. But the problem is like they have low efficiencies and they also have these stability issues. So this paper mainly wanted to study more about like how do we improve the stability of these perovskites by creating double perovskites and alloying them. And I'll come to that. So basically I wanted to go back to thermal. I went back to crystals, and this is just like loose. I just went into the screenshot and I put it there for you to remember, because this can be a simple question. It's like, oh, what is the structure of perovskite? So this is a typical perovskite, has some types in it. So we can have like two different formulations. You can have the A cell where the A is in the center. You can have the B cell in the center. But the basis is this. We have the ABX3, and I already mentioned. So your A would usually be your metal cation. Your B, it can be organic, it can be inorganic. Your B, organic, inorganic, but they are both cations. And then your X is an anion, usually a halide. And this is the coordination number. So your coordination number of A is 12 atoms. It's usually simple cubic if you have the A cell. And when you have the B cell, it is FCC. And you have the B cell in the octahedral side. So, double perovskites. As we see, the simple perovskites are just ABX3, but double perovskites, the B site is split into two. So you have two B sites. So you have a B plus and then a B3 plus. So you have two cations in your B site.
Is that in the center? Can you go to that one?
Yeah, so if you have the B cell, yeah, that's what's going to happen.
So there's like two right next to each other?
Not necessarily. Because of that, the structure is going to change entirely.
Okay.
And I'll show it later. But basically, that's the configuration. That's how they set it up. So you have like B and you have your B plus. I think in this paper they use cesium, sodium, indium, bismuth or something. I'll go back to that soon. But they have the same like coordination number, 12 A sides, 6 B sides still, but then the 2 cations on the B sides instead of 1. And so these are some of the challenges of these, even like the double perovskite. So they have a large band gap because they have another like B cation. There's some lattice distortion. They have this parity forbidden transition, which basically is an optical selection rule which prevents certain optical transitions from taking place. And because of that, their optical absorption efficiencies are reduced, and then the quantum efficiency and all of those things are reduced, and that's very detrimental to solar cells and optoelectronic applications. They also have low power conversion efficiency, stability, and they are also more complex to process. So the aim of the paper mainly was to improve the stability of the perovskites through doping just the B side. And so they mentioned in the paper, you can dope the A side, you can do the X side. And when I went back, because of this paper, I went back to read the crystals part of perovskites. And I remember he actually had examples of doping the A side, or doping the X side, or doping the B side. So they dope the B side with different systems, and they formed alloys. So here, you'd see they have the B plus, they replace the B plus with sodium plus and silver, and then they make the B3 plus indium and bismuth, right? And so they wanted to study the effect of these. They mentioned that most of like the common like just double perovskites, you have maybe cesium, sodium, indium, chlorine. They have that, but they wanted to study the effect of this alloy, and they would show the differences between the pure one and the alloyed one, and then many more things. So their key hypothesis was that the thermodynamics was going to be affected drastically. And this paper is titled Entropy Stabilization. So their point was, in the general thermodynamic equation, we have Gibbs free energy is formation energy minus T delta S, which is the entropy. And they are saying that we want to create as much configurational disorder in the system because of this alloying, that the entropy effect surpasses the formation enthalpy, and then makes your delta G negative, which makes your system more feasible or more stable. And so they used computational tools to do this, which I'll get to shortly. So that was the first thing that they studied. And even though, I'll go to it again, but even though in most of the systems you realize that the formation enthalpy or the formation energy was high, was positive, and the entropy was negative, they had a hypothesis or a study that so far as the formation enthalpy is just tens orders of magnitude above the entropy still dominates the enthalpy, and you get a stable system in your Gibbs free energy. Another thing they studied was their hypothesis was that sodium doping will activate that parity forbidden transition we talked about to increase the quantum efficiency, and indium doping will shift the indirect band gap to direct band gap. So one of the challenges.
I'm sorry. What is quantum efficiency, and how does that do it? Make it better.
Yes. So they have results. They have results, and I'll come to that.
Okay.
Yeah. Okay. I'll come to that. Yes. But basically, the quantum efficiency, as I said, the parity forbidden transition is basically we have some optical transitions that take place. You have a solar cell, or you have a photon coming in, and then it's going to emit some photon. All of those things. But if you have a solar cell, these forbidden transitions means that there are some transitions which will not occur. And one of the rules they had, I think, at the beginning was that the rule for this double perovskite is the system should have an S2 and S2 electronic configuration in the cell, lone pair. And when you have this lone pair in the B3 plus, you are going to activate that transition.
Oh.
If not, they are all forbidden. Every other material you put there is forbidden.
Yeah. I think
So,
the easiest way, correct me if I'm wrong, to understand quantum efficiency is like you are creating excitons, right? So it's the amount of excitons that you create without a recombination.
Yeah.
That's the quantum efficiency. So how many excitons you create
Can you
without recombination?
Okay.
Yeah.
That's quantum efficiency.
Okay.
Yeah.
Yeah, thank you. That was it.
And so like, yeah, this because of that I'll just explain the indirect band gap and direct band gap as well. So direct band gap, you have like the valence band maximum and conduction band minimum along the same
K
line.
vector.
Yeah, yes, K vector.
Mhm.
But then the indirect band gap, you have this it's not an overlap, it's actually a mismatch, and because of that the electronic properties are also affected by that. So they did that, and the last thing they did was to see the effect of controlling the doping. What if we add A amount of sodium, B amount of silver, and just play with the doping? So it's a simulation, so they made different, about 8,000 structures they made, and then they studied the effect on like the band gap and other things. So I will not go into the methodology much because I don't know a lot of the computational studies they did, but they didn't also go deep into it. It's like go read the supporting material, which I did a bit as well. So they use first principles, high throughput calculations to study this system. The model system they used was the cesium, sodium and silver as your B plus, indium and bismuth as your B3 plus, and then your X, which was chlorine, double perovskite system. They made lots of structures from this, and then made different concentrations of this. So basically, they would maybe have 25% of sodium, 75% of this, 75% of this, 25% of this, and then they change a lot to see the effect. So most of the results are based on this. And they use this system which is called special quasi-random structures. And I can send a link about what this is. I had to go read a bit about it. But basically the idea is to construct a model system which is similar to a large-scale alloy system and study the effects of that small model system to see how it closely matches the large-scale system. And so that's what they did, and they were able to get some interesting results. So I'll go straight into the results. So this is the model system they used: cesium, sodium, silver, indium, bismuth, chlorine. And so this is the crystal structure they have. They have the cesium in the octahedral sites. They have the polyhedras of each of these. So like sodium bonds with this chlorine, silver with the chlorine, indium with the chlorine, bismuth with the chlorine. There are different points. I think these colors are very bad because they are very similar if you can't see well. But the bismuth is like somewhere here and all. It doesn't matter too much. But then let's go into the thermodynamics. So this figure B shows the relationship between the formation energy and the entropy. And so for all of these simulations they did, so basically all these dots here are like different structures that they simulated. And they realized that most of these structures had a positive enthalpy, right, as you can see from here. And then the entropies typically were less than 0, right? But then as we increase, and this one they didn't say necessarily whether it was like the entropy were increasing or the temperature, but as this term increased, you realize that the formation energy increases. This is the delta G mark. This is the Gibbs free energy, right? And so as this entropy term also increased, the enthalpy increased, but predominantly less than 0. So what they said here was that for most of these cells, when they started at this starting point here, we have the formation energy being tens of magnitudes just above. This they call it the decomposition line. Basically.
And what is the
they call
decomposition
it,
line?
Yeah, they call it the 0 line, and like above this line, above this line, right? The formation. No, I don't think is this the decomposition line. Now I'm confused because they say it somewhere else. But basically, the decomposition line is the line above which the system becomes more disordered, right? And it's basically beyond that line, they say that the entropy cannot dominate the enthalpy. So I don't think it's this line because they showed, I think it was around 40 somewhere else in the paper. Not here.
Isn't the zero just marking where things are gonna be thermodynamically favorable or not favorable?
Yes.
Okay.
In this paper, yeah. So the decomposition line comes later. I'll talk about it. But basically, yeah. So here, this is 0, and so if you have like your delta G being less than 0, you know, like negative means it's more favorable, right? So that's what they did, and so the delta G was mostly less than 0. So they said that the thermodynamic stability of the system is driven by entropy. As they said, even though like you have the system where when you match up the equation, your T delta S is like, let's say 10, and your delta H is, let's trace it, is also less than 10. You see, like your delta G would dominate your delta H.
So too much entropy, even though in the beginning they said that entropy would like fix things because
Yeah.
of the disorder, to some extent having too much of it would create too much enthalpy as well.
Yeah.
Or is that correlated or something?
Yeah, I guess. Because based on this simulation, as they go higher, and that's why I had a thought like, is this really, because at first I started to think about it in terms of temperature, and I'm like, okay, no, but this is a mixture of temperature and entropy, and we don't necessarily say which is constant, right? But the whole term increases, and as it increases, we have like the gift-free energy also going really high.
They talk about
Yeah.
that they increase entropy.
They
because
increase
they
entropy.
also,
Okay.
when they picked their structures, they picked all structures with the highest formation enthalpy so that they could be able to like really determine the offset. So they
Yeah,
picked the
yeah.
highest possible delta H.
Yeah.
So that when they found a negative Gibbs-free energy, that they would know that it was entropy
Yeah.
that was causing
Yeah.
the stability
Yeah.
direction instead of like temperature.
Yeah,
Some
so
structures that were like purposely more difficult to form.
Yes.
yes.
Okay.
So it means that you get to a certain threshold, like maybe somewhere here, where like once you go beyond it, then your Gibbs-free energy crosses that line, and then you cannot, like, this system is not stable because your
Positive.
formation energy are also very high.
No, I get that, but
Yeah.
I wonder what's causing the increase in enthalpy.
What's causing the increase in enthalpy?
Yeah.
It's
Yeah.
it's you know the main. I'm sorry if I'm wrong.
Yeah, yeah,
the
no.
main equation, like you have delta G, right? In this
Mhm.
case, you are talking about delta G on formation because you are talking about enthalpy of
Oh, but
formation,
then when
right?
you increase, I see it now.
So-
Like if you were to like add that to the other side, then you get enthalpy. Yeah.
So in my case, I always think about delta H as the total energy of the system,
Mhm.
the whole energy, right? All the
Yeah.
energy that you have, and the T minus delta S is the energy that you lose as an entropy. So
Mhm.
delta G, it's the energy that you need to make your process. In this case, the formation of the crystal, right?
Mhm.
So that's why it's just a relation. Yeah.
Okay.
Was I clear?
Yeah.
Yeah, but as you are saying, like the more how do I say it? Like, let's just hypothetically say the more difficult it is to form your crystal, the higher the formation energy or the enthalpy,
Mhm.
and so your delta G is also more positive,
Okay.
right? And so that's what they did first, to just study the effect of the relationship between these thermodynamic parameters. Then they also did a general simulation for the electronic properties. And then the main trend they realized, like at the beginning, we have a very wide range of band gaps. So we have like less than 1 and greater than 3. But then as the entropy increases, as they increase the disorder and the entropy increases, we kind of have like this convergence at a smaller band gap range. So they were saying like this range was between like maybe 1.2 and 1.7 or something. And they're like, this is the general range for single junction solar cells. And so it means that when you are able to increase the configurational entropy of these alloys to this range, you can be able to use them for single junction solar cells.
Yeah.
Then they also studied the effective mass of carriers, and this effective mass of carriers, whether electrons
What
or
is the
holes.
effective mass of carriers?
So basically, in a system, in a semiconductor, you have electrons, you have holes, conduction band, valence band. If like you have to be able to cause your carriers to move, right, to be able
Mhm.
to create charge, right?
Mhm.
And so if your charges or your carriers are denser or have a higher mass, then the mobility is lower,
Okay.
right? And so it's really related to the carrier mobility, right? And so here, what they said was like, you have most of these. So the Me is the yellow one is the electron. This is the holes, and they were like, from the simulation they realized that most of the effective carrier mass of the electrons were less than 1, which means that their what do you call it, mobilities would be higher, right? Now for the holes, they were more dispersed, like, because you see this range from 1 to about 8, but as you increase again the entropy, it converges at a lower effective mass, right? And then the main explanation they gave was like, I was wondering, why are these so low, or even not necessarily just low, but the range of dispersion is smaller as compared to the holes. And they were like, the holes have a wider range of dispersion because the valence band, when they have this like alloying, and they are distorting the entropy, they are distorting the order and then creating more entropy in the system. The valence band is more sensitive. The valence band maximum is more sensitive to these distortions because of the p orbitals which dominate the valence band, as compared to the conduction band minimum, which is more dominated by s electronic states. That's what I read.
Yeah, that's what I saw too.
Yeah, that's what I saw. And so basically that's what they were trying to say here. And then what they did was, after they had like this main system, they had all these structures, they tried to find the best reaction pathway if they were going to have this system. So basically they wanted to see the range of formation energies that they could accomplish if they altered maybe the, how do I say it, the composition of these things.
Oh, yeah.
Right. So they created these 4
The composition
equations.
of B,
Yeah.
of the B side, right?
Yeah. Basically they had these 4 equations, and basically here I was just talking trends basically. So for your equation 1 and your equation 3, you see that as this A term here, the A is just like how many compounds you have of this basically. For this A term, as it increases, your formation enthalpy also increases to this H max, delta H max, and then it decreases with increasing A here, right? And then for equation 2, it's inversely proportional to A. So as you increase A, actually the enthalpy decreases, and then it increases again. But basically, this graph is this plot is showing that within -8 to +8, that's where, if you have any composition of this particular alloy, right, your formation enthalpy is not going to go beyond this point. And if it is -8, the delta H minimum is like your lowest formation enthalpy, which means your easiest path, right? So with this path, you are going to have your entropy dominate your enthalpy very much, and so your thermodynamic stability is enhanced. Whilst when you go to this point here, or when you go to the highest, it's 8. Now they said, and as I mentioned in the first preamble, so far as your enthalpy is just tens of magnitude greater than 0, right, for this system, you are still going to have entropy dominate. So they were saying that for this reaction path, even though this is going to be more difficult, it will still happen, and you can still achieve stability of your system. Right. Now they form these energy contour maps, and they try to study specifically. So in this system, the subscript of sodium is your X, so how many sodium you have, and then your indium is your Y. So they wanted to study the effect of varying concentrations of sodium and indium on each of these thermodynamic parameters, right? And so you'd see here, like, let's say for example, if you're mainly, I think the increments they did were 0.25, 0.5, 0.75, So maybe let's say for 0.25 sodium, at what point, basically what they wanted to understand from this is what are the ranges, what particular concentration should we have of sodium and indium should have to have like maybe very low enthalpy or very high enthalpy. And so if you do this and you find a place where you have very high enthalpy, you avoid it, right? Because you want a lower enthalpy
create
so
a
you
crystal.
can make a more stable system.
Red high entropy? Or entropy?
Enthalpy, yeah.
Okay.
Most of these. So they have values there, basically. So if you have 0.5 of sodium and 0.5 of indium, which is equal amounts, you are in the red zone, 0.04 of your delta H max. That's the highest.
Okay,
Based on
so
these-
red is
this-
highest and
yes.
like kind of
So you
yellow
go. So
thing.
here it's like 0.8 and very small, like 0.1 of indium. You are in 0.005, which is good,
Mhm.
right? So that's what they did here, and then they tried to map it on with like the T delta S, right? And so, like here also, if you have like 0.2 of this, 0.2 of this, they had like these values here to show, okay, what is the value of the entropy term.
Why is the entropy more variable while the entropy is like smooth and pretty?
I don't know. I really don't know. Yeah.
But like, you know,
Isabella, what do you think? Do you have any idea?
No.
cool.
Yeah. Yeah, at first I didn't understand this plot. I had to go come back and I was like, okay, let me try and understand it. And you see like even here with the delta G, like you see like it's also like very less variable because like as we were saying, like there's even a red, there's a green here, there's a red here, right?
Yeah.
But here there's no red, meaning as I was saying that even though like 0.04 is like the highest delta H max here, when you come to the delta G max, the entropy is still going to like be able to dominate the enthalpy and you're still going to have some stability. So it's not like you are in a very red zone, but it's going to just be more difficult as compared to if you were somewhere here. So you do that same correlation with like the sodium content and the indium content. So then they went on to, and these are the more interesting trends that I saw eventually. They studied the effect of varying the B plus site composition on the thermodynamic properties. So what they did here was they kept the B3 plus site stable. Yeah, they kept the B3 plus site stable, so indium bismuth is common here, and they just varied the B plus, right?
Mhm.
And they studied the effects. So this is delta, the gray line, the gray is delta G, the blue is delta H, and then the red is the entropy term. And so what they realized is like you see this trend here. Mostly the first thing you realize is that the delta G follows closely the trend of delta H,
Mhm.
right? So you see like delta H go this way, delta G also goes that way. This delta H goes this way, delta G goes this way. Same here, right? Now one thing you'd realize in all of these is that like still your delta G and your delta S are still again below this zero line, so it's more favorable. Now one key thing that I realized here was like why is it that like these plots are very different, right? One thing you'd see is that like as you increase, as you change these values, say here they both have indium, right? And here we put like very two similar stuff, so sodium and silver here. So the enthalpy of this sodium silver and silver indium alloys was greater as you increase or as you vary the composition as compared to these guys. And then as I studied, I realized that it was actually because of the difference in ionic radii, right? If you study, then I just like got these values out of the internet. Like sodium plus has a ionic radius of 1, indium is 0.8, silver is 1.15, and so I calculated the difference, and you realize that this system has a smaller ionic radii difference than this and this.
Is that
And so
radii or lattice parameter?
it's No, it's not. It's not
Maybe
like
it
this
is
way.
small.
It's ionic radius.
Okay.
Yeah, I just like it's ionic radius. Basically. So basically, what that means is like when you are fitting like your sodium, let's say for example, it's easier to put these together in your system, right? As compared to these guys and these guys, right? So configurational entropy is affected, and again that's why like formation energy, how easy it is for you to form these and this are also affected. Now why exactly this, like when you have let's say delta H max, let's say sodium to be 0.75, these values here, the X is the 0.75 which is sodium, and the Y is the indium. So if you have 0.75 of sodium and 0.25 of indium, I don't know why there's a big spike here. I was wondering. It's something they might ask, but yeah, I really wasn't able to figure it out, except mainly that like these guys have high ions because of the ionic radius. Maybe you could use it, but I think that if they did energy contour maps of these guys like they did for the other ones, we could check, and we can actually check 0.75 and 0.25. Let's see. So sodium is 0.75 and this is 0.25. Okay, let's say somewhere here. It's not really bad, but it's not like the worst thing.
That's a different compound.
Yes,
right?
yeah, that's another thing. So like if they did energy contour maps of like all these compounds, then maybe we could see something.
I have a question
Yeah.
on why they chose for the B plus site to vary. This
Yeah.
is now B plus, right? Because they were using that for B3 plus.
Yeah, they use them interchangeable.
But why?
And so, yeah, and I think the next result actually shows
okay.
that because the indium can actually tune the band gap.
Oh.
And they would show here, yes. So here, what they did was the effect of varying the B3 plus site. The
So
first
that's
one
the
is,
B3 why did they? So for the last one, they added it in the B plus site.
yeah,
So if that doesn't have anything to do with the band gap and they're energetically less favorable,
Mhm.
why choose indium for B plus site?
well, yeah, for that specific one, I don't know.
Okay.
So, but maybe they just wanted to mix things, I don't know. But like one of the recommendations they gave in the paper was like, yeah, you can actually do these things with different like elements
Sure.
and see.
Okay.
Yeah, but I think mainly the indium point was basically this band gap tuning, which I realized. So yeah, you read this paper and you can realize, okay, maybe indium is like my best material for this, right? In my B3 plus side, and maybe sodium is my best material for this in my B plus side.
Okay.
And then if I put the two together, I have direct band gap. I have this forbidden transition because I'll come to that to being broken, and then you have a better system.
So why not just make a perovskite? Because right now they have 4 different materials they're alloying.
Alloying, yeah.
Yeah. So.
The alloying is to improve the configurational disorder.
That was to make a point.
Yeah.
Okay.
That was
so
to
they're
make a
not doing
point.
that, like in whatever material they end up proposing, they're not going to have 6 different elements. They're going to.
They don't propose something at the end.
Oh.
They just say, because it was the thermodynamics they were looking for. They were saying like, based on all these things we've studied, if you do this, this is why you're gonna get this particular, maybe indium does this, sodium does this, that kind of
Okay.
thing.
Okay.
Yeah. And so here, like again, they have these different alloys that they put up together, and then they study the band gaps, right? And so here you'd see this has an indirect band gap, the conduction band minimum and the valence band maximum are not overlapping. Here they overlap, here they don't overlap, here they overlap. What's the similarities between these two? They have indium here. So basically they said, okay, if indium is in the B3 plus site and is causing a direct band gap, what if we take a system, because these are pure, actually, these are not alloyed, right?
Right.
So now what if we put this in the alloyed system? But instead of like just keeping it in the alloyed system, we increase the amount of indium,
Oh.
right? And so as they increase the amount of indium, so you realize from here you have a mismatch, right? You have an indirect band gap when indium is 0.25. But as they increase the amount of indium, they come to a direct band gap situation.
Why is are the bottom ones colorful and the top ones not colorful?
Which ones? These
Like
ones?
just the plots. Like, what's the difference in how the plots they do? One
Well,
line and
yeah, I don't really know. Maybe it's because like, yeah, maybe the simulation, and because this one they just stuck to the same system and they were increasing only the indium. They wanted to show. I don't necessarily know why. Maybe also like this scale bar here just to show things clearly, but I don't know necessarily why they did it. This is a pure system, and maybe for this too they could just get like the values either experimentally or whatever. But this they did like simulations for it.
So the simulation probably can't get those, like, what
Yeah,
actual bands
probably.
look like.
Yeah.
So it just gets like maximums and minimums.
Yeah.
Yes.
And you see like whether like the positions.
The important
so
bits.
one is the most probable to happen.
No.
Which one?
What does red mean? What does red versus
Oh,
blue mean?
sorry.
I mean, there is less likely to be things there for zero.
Mhm.
Yeah, that's a good one. That's a good one. I really don't know. Basically, I was focusing on like the structure, like
It says unfolded
This one.
electronic band structure.
yeah, I was looking at like the conduction band minimum, the valence band maximum.
Oh,
I didn't
yeah.
care too much about all the things that were happening.
That story
underneath
makes a
there.
ton of sense.
Yes.
Yeah.
So I'm like, okay, this is the conduction band minimum, and they show it because that's like what they want you to see.
Right.
Like that's what they want you to focus on.
Yeah.
And this, yes, but as you
Isn't that-
increase, yeah. I was wondering, yeah, you have to
Maybe
explain
yeah,
this.
maybe one is where is more probable to have the band, like
Okay.
conduction
Okay.
or balance, right?
Yeah.
So
probably.
because here we have different amounts, so we don't have a normal band, you know,
Yeah.
like maybe
Because-
you have a mixture of different bands.
mixture.
And the red one,
Oh, it's the
should-
average.
yeah, the red one is the most probable.
It is a probability.
Yeah, maybe it's the most probable
Okay.
band that you have for this specific ratio.
Right.
And then, yeah, go ahead.
The top one is like the band structure,
Mhm.
is what we
Yeah.
calculate based on that kind of stuff. The
Yeah.
second one takes into account the wave function.
Mm.
So
Yeah.
Yeah,
if
yeah.
the wave function of
Wave
the
function.
cell can obtain unfolded band structure, then would be well, the same stuff.
Yep.
So yeah, probably.
It's probability.
Yes. So basically, what they said here was like that the electronic band structure could be tuned with like alloying. So basically, yeah, if you want like a direct band gap, you just like have your alloy system and you add increase the amount of indium, and then you can get this. And yeah, they said like indium has this NS2 lone pair, which can help you get through. Now, this is where this is the last but one figure they had. They compared the electronic properties. So basically, this was the band gap,
Band gap.
and this is the carrier effective mass. And what they studied here was the effect of this multi-element alloying on the band gap. So this time they didn't just take one system. This is for the pure phases. So this one you just have one A side, one B plus, one B,
One
B3
X.
plus, one X. But these are the alloy systems, and they pick a couple. I don't know why they chose these particular ones because they have studied more. But these basically here you realize that based on how much of your X and your Y you have like varying band gap values. And so they said that from this study, you can tune the band gap of your perovskite material just based on the alloy system. And so if you have this, okay, maybe you want like a
You had
low
the whole
band gap.
time and you just brought that out? I'm sorry.
Where have you been keeping them?
Yeah.
I know, right?
Because I remember
I'll
what.
take an orange.
Yeah.
Thank you.
Yeah.
This
That's
is
good.
tangerine,
Yeah. Wait, what
Wait, there's apples too.
an apple.
Sorry, I'm sorry.
Yeah, no
I
worries.
think I didn't bring.
Yeah. So basically
I
like
forgot I had 20 oranges.
Oscar is We're almost done with this presentation.
Yeah, I'm so sorry.
If, no worries, no worries, no worries. Yeah. So if you want a low band gap, you just like take this system, make sure that you have high amount of silver and like 0.5 of indium, and you could get like 1.04. So basically this just shows that you can tune the band gap as compared to like these pure phases, like the band gap varies a lot with these pure phases, but these guys, even like with just one system, depending on the amount of silver or indium you add in which side, you could tune the band gap. Now this second one chose the effective carrier mass, and it took me a while to understand this as well, but the point made sense. So basically what they did was also study the effective carrier masses, and as I mentioned, that's really related to the carrier mobility. And so in these systems, so these ones show that these are the pure phases, and these are the alloyed systems again. And in these systems, what they mainly realized was that the ratio of indium and bismuth dictates like the effective carrier mass, and this is because they yes, from atomic orbital projection. So they had these values, they superimposed it into the atomic orbital projections they had of each system, and then they said that the indium is characteristic for the conduction band minimum, and the bismuth is characteristic for the valence band maximum. And so because of that, because like even though you have silver and the other things there, they are common in both, and so you have just like indium dominating the conduction band, and then the bismuth dominating the valence band. And so one trend I realized is that the fraction of indium, because it dominates the conduction band maximum, is inversely proportional to the mass of the electrons. So what that means is like in this system, for example, okay, I highlighted this, so I'll talk about this. So indium, so this shows X and Y, right? So sodium is X, so sodium is 0.25, indium is 0.75. So if indium is 0.75, it's high, right? Which means that the mass of electrons is going to be low. And that is true because the mass of electrons is the yellow one here, and the mass of the holes is this one here, right? And it's vice versa because the fraction of bismuth would be inversely proportional to the mass of the holes. And they explain this in the sense that when you have a high amount of indium in the system, it's going to cause, basically these delocalization effects. So if you have a high amount of indium in the system, there's going to be delocalization in, how do we call it? The conduction band, right? And so the electrons are going to move about, which means that there's high carrier mobility, right? Then there's going to be localization in the valence band for charge neutrality, basically, or whatever we call it, to combat that effect. So there's going to be localization in the valence band, and because of that, the mass of the holes will be higher because they are localized. They are not as mobile as the electrons. And so because of that, they will have a higher mass, and then the electrons would have a lower mass because of the delocalization in the conduction band.
Okay.
And same thing for like the bismuth, right? So that's how this plot is explained. That's how I understood it.
Wait, so if
Yeah.
there's more bismuth in the material, that means since it's at the valence band, more of the p orbitals of the bismuth are involved in
Yeah.
bonding,
Mhm.
but you have more holes.
So,
I guess
so
there's more
basically
holes
they said,
filled.
so if there's you have more bismuth in the system,
Yeah,
they are saying that there's going to be more delocalization
at the valence band.
at the valence band.
And therefore the mass of the holes is less.
It's less.
Okay.
Yeah. And so there would be more localization in
At
the conduction band.
yeah.
Right.
Okay.
Yeah. And this is the last thing they talked about. So yeah, I had to read this twice, but then I finally got it. So this they finally tried to study the optical properties of these systems, right? And so they studied the transition dipole moment, and I didn't know what this means, but now I do. Basically, it relates to the optical absorption. Maybe you can go read the definition, but it's mainly relevant for optical absorption. So a high transition dipole moment means that the material just has a higher optical absorption, and if it has a low transition dipole moment, it has a low. Yes.
But they use some magnetic field or something to do that?
You
Because
said?
if you're talking about electric dipole, okay,
Yeah.
okay.
So in this system, what they show is like this shows the pure phases. But what did we realize? They showed 6 pure phases, but only one of them has a transition dipole moment. Very high. The rest of these do not have. Why? Because of the forbidden transition.
The Indian, the
Yeah.
indium and BI
Yes.
have the lowness.
The indium and BI, yes. So here they show that like the indium and BI have to be paired together because of their lone NS2, and that's going to activate the system. Now here you realize that in all these alloys we have some indium and some BI somewhere in there, right? So even though they might have low transition dipole moments, they still have. And so depending on how much indium, how much bismuth, they can also tune the optical absorption of these materials, right? Now my only argument is like this has really a very high optical transition dipole moment or optical absorption. So like there's really no need, right? But then if you go back and you compare the other things like the band gap and things, it's relevant for you to actually do this. Basically because you want to tune. Now the last thing they studied was like these absorption spectra, right? And mainly what they were looking for is how the electronic band gaps correlate with the absorption.
But say it again. For me, it's not clear.
Which one?
Like we are looking with the transition dipole moment.
We are looking for high absorption, optical absorption.
So for high transition dipole moment,
Yeah,
okay.
high
Okay,
high
okay.
transition dipole moment corresponds to high optical absorption.
Okay,
Now
yeah,
the thing is
okay.
even though we just like we have 6 pure phases, right? But only one has a
Yeah.
this transition
why.
dipole moment. Why don't these guys have? Because of the selection rule, the
Yeah,
parity
selection rule.
forbidden transition, right? They do not satisfy the requirements. They do not have this indium and bismuth in their B sites, right? B plus, yeah. Like there's more technicality in it. Like they talk about the fact that there's NS2 and then you need to have like a pair of odd and even symmetry. There's a lot of things I was reading about it, but I'm not versed in it too much to go deep into the forbidden transition. But basically that's what the reason why these guys do not have. But in solar cell applications we want high
Because
absorption.
it's you know, but the difference is crazy. Because if you notice,
Yeah.
it's go like from 0 to 15 and then 450.
Yeah, that's really
And-
rare.
Yeah,
And
yeah.
so that's
very
mean
different.
like the mixtures, you know, when you have different concentrations,
Mhm.
if you use into account the transition dipole moment,
Yeah,
are not useful.
are not useful. In
Yeah,
terms
because
of,
we are looking for high absorption, so high transition dipole moment.
Mhm.
So the
Yeah.
different concentration one.
I think the
the
question would
difference
be-
is really high
Yeah.
because it's 15 and then 450.
Yeah.
Yeah, but the
Right?
thing is, it depends on how high do we want. And the thing is, like, all these other guys do not even have anything.
Yeah,
Whether
yeah.
it's 0, it's not like they suppress the graph for this thing to be so high, right? Even at 0, none of these pure phases have a transition dipole moment, right?
Mhm.
So they are trying to say that, yeah, even though, imagine like we have only one element, which is a conductor, right? But we need conductors to do a lot of stuff. What if we can take some of the materials which are insulators and make them conductors and have a lot, even if they don't conduct so much? Do you understand? So it depends on application basically.
Yeah.
But they were able to achieve something, right?
Okay.
That's the point. And so lastly here, what they tried to do here was like show the absorption spectra, and again this time they showed 4 pure phases and they showed all the alloys here. And what they showed was these curves are the absorption spectra, and these arrows here are the calculated electronic band gaps. And for there to be, basically what they try to show is like if there's an electronic band, if they calculate the electronic band gap, right, usually that is the value, and that is for only the pure phases basically, right? They wanted to correlate that with the absorption spectra, and if they overlap, that means that you have like similar, what do you call it, structures in there. But what happened is, because of this, what do we call it, the forbidden transition being broken. So they use this to confirm that there's some breaking of the forbidden transition, in that like this value, when it falls on this axis, doesn't overlap with this arrow. Same with this, same with this, same with this. So there's like some how do we say it,
Pretty funky going on.
yeah, the word isn't coming, but basically these are the alloys, and it shows like for these alloys, most of them overlap with their calculated electronic band gaps, and they try to show that basically the forbidden transition is broken in a way due to reduced symmetry. And I can explain this in terms of crystal structures, basically in that we want like NS2 lone pairs in the pure phase. We want indium to have this and bismuth to have this for us to be able to activate that optical transition, right? But in these alloys, because they have been alloyed together, there's been some disorder in the system, and the disorder makes the system have a higher entropy in terms of thermodynamics, but it also reduces the symmetry of the system. Does that make sense?
Yeah.
It reduces the symmetry of the system, and they are saying that because it reduces the symmetry of the system, some of the systems which shouldn't have an optical transition start to show optical transitions. Yes, that's what they prove here, and that's how they show the overlap with the electronic band gaps. So they show that, and let me just confirm from here. Yeah, because of that break in the symmetry, because of the alloying, they are able to achieve that what do we call it, breaking of the optical transition, which is important again for the optical absorption. So mainly that's what they try to investigate in this paper. They investigated the thermodynamic stability, then they investigated the effect of B-site alloying while keeping B3 plus constant, then investigated the effect of B3 plus while keeping B constant, and we saw like with the trend, indium was able to increase, like change the band gap from indirect to direct. Then they showed that you can tune the band gap by alloying differently. You can also play with the effective carrier mass, and they showed the relationship between indium and bismuth in that regard, and then these optical properties. So
Wait, before you go on,
Yep.
I have a question.
Yep.
So only the ones that are not alloyed have a difference in the electronic band gap and the optical
Yes.
absorption.
yes,
And those have more symmetry than alloyed ones, correct?
yes.
So why is there a bigger difference? Because then you just say that the increase in alloy creates less symmetry, which creates a difference.
Mhm.
I guess that's why I'm confused.
Yeah. So here they show like, so this is the calculated like electronic band gap,
Yeah.
and this is the result from the optical spectra that they had. So this is for the pure system here. This one, I
Yeah.
think.
The
Yeah,
blue,
one of them
green,
here, and then the red.
Yeah.
Right. Now these ones, what do they call them?
Those are for all the other alloys.
These are for all the other
Those are
alloys.
spot on.
Alloys, yes, and those are spot on. So what they try to show, and I think I should have a better explanation for this, but what they are trying to show is that electronically, right? You see, the electronic band gap configuration should have nothing to do with the optical transitions that are going to take place. Not necessarily.
No, yeah, that's what
Yes,
I. Yeah.
not necessarily.
Yeah,
right?
because if you notice, so for example,
Yeah.
in the second one, the red line,
Mhm.
the electronic band gap, it's 1, right?
Mhm,
So
yeah.
it's the lowest one. So that means the absorption should be amazing, right? It's
Yeah.
the lowest energy.
Right.
But the red one there is no that transition dipole moment for the red one, right?
Mhm.
The red one is the sodium indium, or which is
Yeah.
so
No,
there
the
is
red one is silver indium.
silver indium,
Yeah, this one.
It does not have an
anything. So you know,
Oh, I get what
So-
you're saying. So it might not have. That doesn't have anything to do with the arrows.
But this is actually crazy.
yeah, the arrows are the electronic band gap. What do
Right,
you mean?
but that's my question. Why are the arrows not on the same marker for the pure phases, whereas for the alloy phasers they are on the same marker? Not talking necessarily about the transition dipole. Or I guess on the right, because that's
Yeah, I get the question. I get the
Okay.
question.
cool.
And let me
I
see
don't
if
understand the
there's a
question.
better. Let me see there's a better explanation in the paper. But I have.
This is why I didn't choose this paper.
This paper is crazy.
This is wild.
Yeah.
Like, this is a whole thesis right here.
I mean, different concentrations, different structure, different electronic structure, different band gaps. Well, that's why arrows are in different positions, right?
Wait, what's your question?
So in the paper.
That's the question. Yeah.
Yeah, so she's like, why is it that like we have this difference, right, between
Oh.
the electronic band gap and then the absorption spectra for
Because there's more symmetry in the material, or like there's less disorder.
Oh, okay.
So the reduced symmetry really got me, because I was like, that doesn't make any sense. I see reduced symmetry as increase in chaos or increase in entropy.
Mhm.
And so when they're saying like, they
Yeah.
keep saying reduce symmetry, that
Yeah.
means they're just like, that's just more alloy, more entropy.
yeah, that's
they're putting
more
into the system.
alloy, yeah.
And so these pure phases, or the pure ones that they have, that means is there's better symmetry, so there's less entropy, and so therefore their optical and their electronic band gaps don't match, which makes them basically poor optical
Yeah,
things.
for optical
You
devices.
want them to match. So then they show that when you actually alloy it, you have reduced symmetry or more chaos or like more entropy in the system,
So
and that
that's
allows for the
optical and
electronic band
electronic.
gap and the optical band gap to match, with give them good optical properties.
Mhm.
Yeah,
Okay.
So
That's
the
an
reduced
excellent
symmetry
point.
was like,
yeah.
I don't know. I had to keep like
Yeah, I
rewiring
think you
my
have
brain
to go
think
back.
like,
Yeah, you have to go back.
because in my head symmetry is good, and it kept saying like reduced symmetry, and I was like, that's just more chaos, and so I just kept saying more chaos because that made more sense to me. But
Yeah, but the alloying, well, maybe it's good, but it's still like disrupting the normal system.
yes,
Yeah, which is reducing the symmetry. Yeah, so in the paper, what they actually say is that the optical band gaps of the alloys are nearly equal to the calculated electronic band gaps, which implies a strong optical transition between the band edges. So, like, I think how they should have shown this is like, show this without the alloys, and then show it with the alloys,
Yeah.
and then you see the difference, because these are systems, these pure systems are what you start with, and then they are bad, right? But then once you alloy them, now you are getting like closer to like better optical transitions, and that's why they compare it with these guys. Because I was gonna ask, why didn't they show the cesium, indium,
Yeah.
bismuth, chloride? Because it was actually good.
And
right?
actually, which
It's
one of
good.
them? What if the pure one is the direct band gap? The Indian one, right?
Maybe it didn't do
Yeah,
it.
it's a
The direct band gap
direct band.
Direct
Yeah,
one.
indium.
is there. Which one is the Indian?
I think
the
this one.
INBI,
No,
yeah,
no, but which color here?
it's not there.
It's not
It's
there.
not-
That's what I'm saying. It's not
That's
there.
no,
So they
that's
are
what
trying
I'm
to show
saying.
all the bad guys
Weird.
and say,
Yeah,
okay.
that's weird. Why they didn't show
But
the
that's the
direct
tough
one?
part with these materials, with these like double or like these perovskites, is that they may have good direct band gap, but then they have like really poor stability in thermal conditions. So they have
Yeah.
really good stability in poor
Yeah.
conditions, but they have really poor optical things. So it's like it's really hard to
It's
get
really-
a
yeah.
really good match across all of them. Which is why I think that you're mentioning, showing that the like indium, the INBI one is really good for this dipole moment, but like it's probably really, really unstable in any thermal condition.
And
therefore
which
that's
is the blue
probably
one?
it's not
The
And I
blue
think
one
they
is
don't show it here. What? This blue one?
Yeah.
The blue
Cesium,
one is the,
silver.
yeah, this one, right?
Is this one? Let's go back. Let's go back and see something. Let's go here.
Yeah, exactly. So
Yeah.
that's what I'm saying. So here in the ratios,
Yeah.
the only direct band gap is the one with the more indium, right?
Which
Yeah.
one?
In
This
the
one?
ratios. No, not
Yeah.
there, not there.
This one?
Yeah.
Yeah, this
Here.
one. This is the alloy. This
Yeah.
is actually an alloy.
Yeah.
Yeah.
So, but according to this,
Uh-huh.
the more indium, all of the others, according to the simulation, the band gap is not necessarily direct band gap, right?
Which one? This one?
The Indian one, I don't know. Let's see which one is
Yeah,
the
you see, like I was trying to compare like these alloys to the other ones. Can you see like?
It's tough because they like
We-
have this such range of alloys, and then they pick and choose
Yeah,
which
they
alloys
pick and
they
choose
wanna,
which one
They
want
wanna
to
show
measure.
and
they
that's
want to
it,
show
yeah.
for different
That's the
stuff,
thing.
which was really hard because it was like they're like, but these concentrations are really good for this application. But then they
Sodium,
pick a completely
sodium,
different set of
silver.
alloys to then go over optical properties,
Yeah,
and then a
yeah.
completely different set to go over like enthalpy. And it was like kind of
Yeah,
confusing.
because they showed the sodium indium in the other one, which has an indirect band gap, right? No, it actually has direct, but it doesn't have a transition that moment here. This one, right?
Because probably because the
Yeah.
band gap
Yes,
is too,
it's
the
crazy.
band gap is too big.
Maybe.
You have to have a small
Yeah.
enough band gap. The video taught me you have to have a small enough band gap for the electrons to like
Yeah,
jump through and then have
yeah.
optical properties.
Yeah, like for this one, yeah, I was like, okay, maybe they want to say like this guy is too good to show what they want to show here. So let's not put it there so
Yeah.
that we can show all the bad guys and show that the alloy makes them good.
And they don't mention like excluding it at all. Like in the
Yes, they don't
paper.
mention like if this is the first time I'm actually paying
So that's why I'm
attention
like,
to
people that review these papers for publication, I'm like, do those people have these questions? And I'm like,
Yeah.
wouldn't they have said like, hey, why didn't you include this? But
Yeah. Well, yeah. So that's what they
Nobody's
do.
reading this. Nobody actually looked at this.
Yeah.
Ooh, grass. Looks good.
So relevance in core classes, I think
Crazy.
they will talk about like entropy of mixing. They mentioned it a lot in the paper. Basically, just that primary equation, and I think that they can go many ways. If it's Gokli, he can actually ask you to draw the delta G versus delta T. Which one did he give us in the exams multiple times? The delta G
that
versus
sucks.
what graph? You have to draw the graph. The phase diagram. I don't know. Yeah. The how does like the entropy affect the Gibbs free energy? Like they could talk about this. Like explain maybe in one of the graphs how this affects this. And basically, this paper took the concept of high entropy alloys, which is not necessarily used for perovskites, right? It's used for metals and other things. So how does it achieve entropy stabilization in these perovskite systems? And through the results, they show that, right? That as we are talking about like reduced symmetry and all of those things, we are able to increase the entropy, reduce the delta G. So in terms of crystals, stuff can be asked about like the perovskite crystal structure in general. The symmetry reduction, as we are talking about, like how like does it affect stuff? I don't know what kind of calculation question can be asked about this, but I think it would be mostly like theory, like written like how does this symmetry reduction actually even affect things, and maybe if it was this other system we studied in class, how could it be affected? Because I remember like if we take like the like normal crystal systems that we deal with, when we talk about like cubic is like very like has like high symmetry, and then when you go down to like triclinic, it has a reduced symmetry, so you can compare those things and talk about some stuff. Because like when you even talk about like perovskites in general, because of their instability and stuff, like last semester as we studied, when you increase the temperature, they change. It can change from like orthorhombic to cubic, and then to something, and hexagonal or something. And because of that, the optical properties also change. You can go from a black phase to a yellow phase, all of those things, and affect the property. So it's like now relating it to crystals, maybe if a triclinic phase was introduced, why doesn't it then have better properties, like something like that? In this paper, they actually show that the symmetry reduction is beneficial, but then in most cases it is not. And so maybe they can ask, okay, the symmetry is reduced, and let's say the paper, the crystal was cubic, and you apply an electric field in the A direction, what are you gonna get? Because the symmetry is reduced, like something like hypothetically. Yeah. And so
Always.
it's like, okay, where was the cesium sitting in there? It's like, is it in the tetrahedral side or the octahedral side?
Yeah.
No way.
Yeah.
That'd be cool.
And then like they talk about defects briefly, and they were like, okay, we are talking about like symmetry being introduced, symmetry being reduced, but also we are applying a lot of like disorder into the system. So does defect play a role or not? And then the paper says like, yeah, there could be vacancies and interstitials and all of those things, but these papers, they simulated them they tried to simulate them between 800 degrees 800 Kelvin to 1200. Was it Kelvin or degrees Celsius? I don't remember, but one of them, and they realized that there was not much change from going between 800 to 1200. Maybe over 1200 there was more change. And so they were saying like, at these lower temperatures the defects don't play a major role, or they are negligible for their study. That's what they said. And so basically that's what I learned from the paper. I don't know. Yeah, I had a lot of questions actually. So like they did computational work. I'm like, how do these first principle, high throughput calculations work? I'm showing the supporting information. I didn't read from the beginning. I read some other parts where they explain other things. Maybe they talk a bit about this. They talk a bit about the SQS approach, and I think I explained this. So it's called like the special quasi-random structures, and they try to just like simulate a smaller structure representative of the bigger one, and they try to see how it mimics the properties of that, to be able to identify the properties they're looking for. What is this parity forbidden transition? Why does it occur, and how is it broken? They could ask, how does indium doping cause the shift from the indirect to the direct band gap? Yeah, it's more about like the electronic structure and stuff like that. Why are double perovskites used and not single perovskites? Yes, because they could talk about that. And what is the transition dipole moment, or like that particular graph, right? Why is it important for this study, and why is it zero for the pure perovskites? How do you interpret the energy contour maps? I think that was figure 1, and what are their significance? They're basically telling us that we can have regions of stability, high stability and low stability for each of the thermodynamic parameters, depending on how much sodium X or indium Y we have in the system. And how does the crystal structure of the double perovskites change with the doping or alloying? They didn't talk about that, but I think, as I was mentioning, maybe if this symmetry is broken and we assume that they had a cubic structure, and let's say that the doping is like applying this particular field in this direction, what's going to happen at that time? And what are the point groups for perovskites? I don't know.
Yeah.
These are just like wild questions in my head.
Something I could see them saying, or like potentially, is like I think we learned in thermo and learning Christo is like there's the 5 things you have to consider when you're doping and stuff like that. And it was like
rules,
ionic radii. No, it was
solubility,
like the solubility, ionic radii,
electronegativity,
electronegativity,
yeah.
valence, and stuff like that. And I could definitely see being like,
Yeah,
okay,
they
you're
could ask-
doping, or like you're this cation transmutation. Like, what are the 5 rules, or like
Yeah,
what do you have to
solubility
consider?
rules, yeah.
Especially because they mentioned electronegativity and the ionic radii here. in
Ionic
this.
radii, yeah. They could
Just
ask.
review the doping.
I think so.
Review
Yeah.
doping from crystals.
Yeah.
Yeah, it's also in
and the
thermo.
first principles high throughput calculation is like, I don't know how like exactly the software works, but it's like you basically put in, it's be able to like predict and analyze properties of materials just based off of fundamental laws. So they're just like inputting in like first like all the
Just,
basic like
basic
thermo
laws,
laws, and then it's like,
equations
okay,
and
like these
stuff.
2 materials can't mix, so this is not a viable thing. Okay, these 2 like these 2 ions like don't work, or these 2 work. So I think it's just like they're basically ruling out all possible combinations just based off fundamental laws, and I think there's some program that like knows what to do.
Like, is it a quantum thing or just a classical? Is it a quantum thing, or like, does it not know that much?
I have no clue actually.
Okay.
I'm assuming it would, because I
Okay.
feel like there are software out there that's able to like take into account that stuff. But yeah, it's basically allows you so you don't have to do any like empirical data. Like you can just plug in like, okay, this is all the information I have on these materials. Like, will they work together? Will they not work together?
Is that based on like atomic radii?
Yeah, I think it's like you putting in literally everything you know about it, all of these materials, and then it's like basically tells you like whether their interactions are possible or not.
Those
Yeah,
chips are
and,
good.
So
Yeah.
that was my interpretation.
Yeah.
Cool.
Also,
All good to answer
what did I
some.
write down?
Conclusion.
Is anyone doing this paper?
I'll do it.
I probably am, yeah, because it's similar to the other perovskites paper, and perovskites is technically my research. Well, the perovskites part of this paper is the only thing that corresponds with my research.
Mhm.
So it's like,
Nice.
Yeah,
I guess
I'll
I'll
do
do
it.
it,
Straight
but
physics and so much data.
This paper looks kind of
Yeah.
lengthy. There's a huge variety of things going on.
Yeah, there's lots of. I was like, I have to understand every figure in this paper, so
It's crazy.
I go back. But like, if they don't ask too technical questions,
Well, maybe we'll ask really easy questions because it's such a hard paper.
yeah, maybe, yeah. That's what like I'm putting in my pocket. It's my trump card. Let's see.
Or it could be like a really hard paper with really hard questions.
Yeah, if it's hard questions, I won't do it.
True fact.
Oh yeah, at the end of the day, you answer 6, so I answer, but it might not count.
Who cares? Right?
Yeah, are you gonna do the other one?
Cool.
Yeah, I can go with the other one right now because it's related to
Send to
perovskite, right?
Isabella.
Are you doing a fast one?
Fast one?
Oscar, you doing a fast one?
This is not fast one.
Oh,
The
mine
next
is.
one?
Oh, I also
Mine is
mentioned
fast.
Mhm.
for
Yeah.
ionic bonding because they talk about the
Managed
like
to do it,
double
yeah.
Oh.
with the
But
what are
there's
they,
like
what are they
some
called?
knowledge-
Yeah, they said.
gaps
Yeah, I
on
think
the
for why they
still.
use the double perovskites.
So-
Multi-element
Yeah.
halide. So I was like, okay, what the fuck's a halide? And then it was like halogen
Group 7,
elements
yeah. Group
that
7.
are
Es que está todavía.
halogen
Lu-
elements
they accept
bond
an
with other
electron.
less electronegative elements. And so I was like, okay, so there's a complete in ionic bonding. a
Okay, I
complete-
sent to you the.
a complete transfer of electrons from metal
While
to
you put
non-metal.
the
Mhm.
number
So
there,
the
I will
compound of
remember.
ions is held together by electrostatic forces.
Mhm.
Metal cations and halide perovskites, so like the other
Actually, you
non-halogen
read that
thing,
completely.
have low electronegativity difference
Polymer
versus, I guess, in ionic bonding. So the electron transfer is
film.
incomplete,
So fresh.
and then you have an
The
orbital
electron
overlap.
transfer is incomplete.
Incomplete, yeah.
Okay.
Yeah.
So what
And then
happens?
So, like,
orbital overlap
Mhm.
when
You
you,
know what
is
they're talking about
actual
with the
electron
WLF.
sharing.
I kind of understand it. It's like.
And then halide
it's
ions
WLF.
are
I just
highly
wanna know if I'm right or
polarizable,
wrong
which is
with
why I
what
think they
people
mentioned the
think.
dipole
And to
thing.
me, it's like.
Is because
it doesn't follow the
halides
WLF
specifically
because usually it's
have
like
a
time
very
temperature
high
position.
polarization
To
potential.
determine, like
Yeah,
the
I think
I don't know
they
why I
mentioned-
wrote that. I must have been reading this and I was
But
like,
in this case,
I
as I
think-
started getting deeper into the knowledge, I
the
was like, oh
film
crap,
thickness
ionic bonding,
to
okay,
a certain,
covalent bonding, all this stuff. I think
in
when I was trying to figure out what a
nanometer
halide
scale
was.
is
Okay.
impacting,
At the beginning, they were
like,
talking about like.
not necessarily
Thomas,
last
are you
transition.
taking it off?
Sorry, that was loud.
Oh yeah.
At the beginning.